Welcome to State of Simulation, the podcast all about multiphysics simulation, where we stay up to date with what's working, what's not, and what needs to change. Each episode features an open conversation with the engineers and technical leaders shaping the future of physical product development. I'm your host, Jukka Knutinen, and in today's episode, we're speaking with Dr. Yong-Jihn Kim, founder and CEO of Cutting Edge Superconductors. With over 30 years of experience in superconductivity, Dr. Kim has made groundbreaking contributions to the field, including the recent discovery of CES 2023, which they claim to be the world's first room temperature ambient pressure superconductor. We'll dive into what this discovery could mean for technologies like MRI, energy systems, and semiconductors, and why simulation tools haven't kept up with the demands of this new frontier. Without further ado, let's get started with the show. So, to begin, could you just tell us a little bit about yourself and your company? So who are you and what do you do?
Hi, nice to meet you. My name is Yong-Jihn Kim. I am from Korea, and I got my PhD from Seoul National University, and I did my postdoc at Harvard Physics and Purdue University. I have been working on superconductivity more than 30 years, and I discovered some new phenomena.
Yeah.
So I am trying to commercialize my discoveries. So I started a company named Cutting Edge Superconductors.
Yep.
And I am the founder and chief executive officer. And recently, we discovered a room temperature ambient pressure superconductor for the first time in the world.
Right.
So we are the first one which produced room temperature ambient pressure superconductor. And this new material can revolutionize almost all tech industries, like MRI, electric power transmission and distribution, data center, and recently we invented a superconductor transistor. So this one can operate at lower voltage and power consumption with almost no heat generation.
Yep.
And almost no energy loss. So we are excited to produce this superconductor transistor for semiconductor industry. So our superconductor can revolutionize almost all tech industries. So we have so many, market, and we focus on low-hanging fruit, like, so MRI market. So our room temperature superconductor wire can revolutionize MRI. Especially, we can produce low cooling MRI. Suppose we don't need any liquid helium or cooling system for MRI. It can be very simple and efficient and very light. So, and currently we have helium shortage problem. So it can impact MRI market. And nowadays, due to the artificial intelligence chips, we need huge, electric, power. So, the companies are focusing on, nuclear, source. And then our superconductor has a zero electrical resistance, so it can save so much energy. and there's no heat generation. So the computer, cell phone, they can be much safer.
Okay, so well, that was a very comprehensive overview. So you said that you are trying to commercialize it. What's the status right now? Are you working with any pilot customers, or are you still sort of in the R&D phase, like purely in the R&D phase?
So right now, still we are doing R&D, and we identified the composition of our superconductor. So we are ready for mass production, and especially this month and next month, we are trying to produce 100% pure room temperature superconductor bulk samples.
All right.
So that's the current our most important project, and then we are moving to prototyping of product like electric wires, and we are also working on printed circuit board for wireless communications. There's a company in Puerto Rico. They are working with our company for it is called the Wilkinson Power Divider PCB printed circuit board, and I am trying to how can I say get collaboration with the semiconductor chip industries. So we are talking to major semiconductor chip industry to work on our superconductor transistor.
Got it. Okay. Well, one of the sort of key questions here is that when you are doing this quite intensive R&D, what is the sort of relationship that you have with simulation? So is that an integral part of this R&D that you are doing, or is it sort of a add-on or even less? So what is the sort of relationship there?
Yeah, the simulation can be very helpful for our R&D also, product development. For instance, we noted that there's no simulation for superconductor levitation.
Right.
So, and especially superconductor shows levitation below a magnet is called quantum locking. So I think you saw that quantum locking demonstration of low tissue or high tissue superconductors. But if you can have a simulation tool for levitation and quantum locking, it can be very helpful for our product development. Especially, we need to find the more details of the levitation condition and the quantum locking condition, depending on our sample size and the purity. So if your company can produce, simulation tool for levitation and the quantum locking of superconductors, that can be very helpful. And
right, Oh, sorry. We can definitely get into that later. I think what would be interesting to hear is that what is working for you right now. This podcast is brought to you by QuantScience. If you're working with multiphysics simulations that feel too slow, limited, or rigid, QuantScience also might be a better fit. It's a cloud-native platform that lets you run complex simulations faster, scale as you need, and automate your workflows. To see how it works and request a trial, visit quantscience.com. Again, to see how it works and request a trial, visit quantscience.com. So you said you are doing some sort of simulations. So what kind of simulations are you conducting successfully right now?
So we are thinking about using probably MATLAB or Mathematica, because there's no simulation tool right now So we are trying to develop our own simulation tools using
Right.
the MATLAB or Mathematica or some other, you know, tools. And so we are kind of, so we don't see the, you know, the simulation tool available in the market right now. So we see that we need to develop it. And
Right.
another issue is, as I said, we developed a superconductor transistor.
Yep.
And I'm not sure whether there's a simulation tool for MOSFET. You know, that's the building block of a semiconductor transistor. It's called the metal oxide semiconductor field effect transistor.
Yeah.
And in our case, instead of metal, we can replace metal part by our superconductor, and also drain and source and gate. So we named it superconductor oxide semiconductor field effect transistor. And it can be very helpful for semiconductor industry. So we want to see the, you know, size effect, especially in the transistor. Smaller size is better. So we can simulate how the smaller size can be, you know, I mean, it can be impacting the performance of our superconductor transistor. So basically, we have two subjects for simulation.
Yes. So okay. So could you maybe open up a bit to me that or sort of talk it through? So what exactly is missing? So what kind of features are you sort of not seeing in the existing simulation tools that don't serve your needs? So what is it that the current, since there are plenty of tools out there, so what's missing in them so that doesn't serve you?
For the superconductor levitation and quantum locking,
yeah,
I don't see any available software in the market. I don't see any software, and there is some, you know, some theoretical equations for simulating levitation and quantum locking. There are some phenomenological equations for levitation. That is too crude. So we need to have a more quantum mechanical simulation.
I see. Okay, so it's in the theory and the equations themselves where the sort of issue is.
The quantum mechanical simulation. So currently available one can be electromagnetism-based simulation or equations. So we need to work on quantum mechanical equations. And for the superconductor field effect transistor, I'm sure in the semiconductor industry, they should have a simulation tool for MOSFET. I haven't tried to find it. I think there should be available, I think, because, you know, semiconductor industry huge, there should be that simulation. But now we need to replace metal part like gate, drain, and source by our room temperature superconductor. So using the MOSFET simulation, we need to change it to allow the superconductor incorporation.
Yes. Okay, so it sounds like you are sort of dealing with a very unique problem, or do you see that? Do you find from what you've been talking with colleagues or others that there are others who are sort of facing the similar sort of obstacles, or is this just very unique to your special use case?
So I think it is unique because there was no room temperature superconductor. So nobody thought of incorporation of room temperature superconductor in the transistor. But recently, I noticed IBM, they have got the patent for, actually they said, superconducting gate transistor. So, but that's for the low TC material. But they have a patent for superconductor gate field effect transistor using low TC superconductor.
Right.
So they see the potential for superconductor in transistor.
Yeah.
At very low temperature using helium, cryogenic system. But now we are saying that, okay, that's good. You can make a superconductor transistor without any cooling.
Yep. Interesting. Very, very interesting. So, it's actually very, very interesting to have this sort of unique case, let alone as in the first episode of the show. That's amazing. So, I suppose that the question or the point is that you don't necessarily see the sort of simulation market meeting your needs anytime soon, which is, I suppose, which is why you are developing your own algorithms. Is that the case?
Yes, that is true. Yeah, but for the superconductor transistor, the market is huge. So I think if our superconductor transistor is well known to semiconductor industry, maybe some companies may try to produce simulation tools.
Yes. Yeah. So exactly. So do you see that there are other companies who might sort of follow in your footsteps and stumble across or develop similar kind of technologies where there is indeed the demand for more tools and more features?
Yeah, I think so, because in semiconductor industry, the progress is so fast. Whereas in superconductor area, the progress is relatively slow.
Right. Right.
Yes.
All right then. Well, that's fascinating stuff. And I suppose I could sort of still ask your outlook on how you see that the field sort of in general, or let's say that within the sort of superconductor space. So what is the direction that you see that the simulation platforms going into? What kind of trends have you perhaps been seeing, if any?
Yeah, I saw your software in your company, and I see that those tools are helpful, but I see that there may be a little bit room for quantum mechanical more accurate, simulation. So I see there is more based on electromagnetism.
Right.
But superconductor is called macroscopic quantum phenomena. Quantum mechanical interaction produce the macroscopic phenomena. So microscopic details based on quantum mechanics is crucial. So there should be some way how to include the microscopic details and based on quantum mechanics, so you can more refine your simulation tools.
Yep. All right. Well, last question that I have for you, which I think I might suspect already the answer to this, but I'm going to ask it anyway. So, if you could wave a magic wand and improve one aspect of your simulation, let's say approach overnight, what would it be?
Can you make your question more easier to understand? I think your question is a little bit ambiguous for me. So
Yes, no worries. So if you had a magic wand in your hand, which had the ability to give any sort of superpowers to your software or platform that you are using, and you could wave it, and your one wish would come true, just a single wish, what would it be?
yes, I mean, if I have a quantum computer,
Yeah.
With all the quantum mechanical many body theory knowledges, let's say I
Yes.
have a quantum computer.
Quantum computer.
Doing all the quantum mechanical many body theories. Then
Yes.
I will, solve all the problem for
Yep.
our superconductor, simulation. So basically, we need the quantum mechanics based artificial intelligence.
I see. Yep.
Mhm.
Amazing.
Thank you.
All right then. Uh, that's as I said, fascinating stuff that you have here, and glad to have you on. Thank you for listening to this episode of The State of Simulation. To stay updated with the latest episodes, webinars, blogs, white papers, and more, join our community of more than 6,000 engineers and engineer-minded people on our LinkedIn page, Quantscience. Thank you once again, and see you in the next one.